Hello and welcome to G Fun Facts Online. Today we are going to correct a mistake that has persisted in science textbooks for nearly 40 years. We are traveling to the outer reaches of our solar system to talk about the seventh planet, Uranus. For decades, this ice giant has been labeled the oddball of our celestial neighborhood. It was considered a boring, magnetically broken world that defied the standard laws of planetary physics. But as it turns out, we were wrong. In late 2024, a massive breakthrough in planetary archaeology revealed that our entire understanding of Uranus was based on a cosmic coincidence of staggering improbability. We didn't see the real planet. We saw a mirage caused by a spectacular space weather event. So let's dive deep into the story of the Solar Wind Mirage, how it tricked a generation of scientists, and why this discovery implies that Uranus might be teeming with hidden oceans and potential life. To understand the magnitude of this recent discovery, we have to go back to the source. We need to look at the only time humanity has ever visited Uranus up close. The date is January 1986. NASA's Voyager 2 spacecraft is the hero of this story, but by the time it reached Uranus, it was a weary traveler. Launched in 1977, it had already survived the intense radiation hellscape of Jupiter and the dangerous ring plane crossing of Saturn. Uranus was a completely different challenge. It sits 1.8 billion miles from the Sun, a realm of perpetual twilight where sunlight is 400 times weaker than it is on Earth. The data transmission rate back to Earth had slowed to a trickle, with signals taking 2 hours and 45 minutes to cross the abyss. The flyby was a high-stakes bullseye maneuver. Voyager 2 had to thread a needle, passing within 50,600 miles of the planet's cloud tops, while moving at over 30,000 miles per hour. Because Uranus rolls on its side, with its pole pointing almost directly at the Sun, the entire system was laid out like a target. Voyager would punch through the plane of the moons, seeing them all in a matter of hours. As the data began to arrive at the Jet Propulsion Laboratory, or JPL, the excitement quickly turned to total confusion. The data was, for lack of a better word, a mess. The first shock was the magnetic field. On Earth, Jupiter, and Saturn, the magnetic north and south poles are roughly aligned with the planet's rotation axis. It works like a bar magnet, spinning inside the planet. But at Uranus, the magnetic field was tilted 59 degrees away from the rotation axis. Even worse, it didn't go through the center of the planet. It was offset by a third of the planet's radius. It looked as if the magnetic generator inside Uranus had been knocked loose and was tumbling around in the outer layers. Then came the plasma data, which was even more baffling. A planet's magnetosphere, the magnetic bubble surrounding it, is usually filled with plasma, a soup of charged particles like ions and electrons. At Jupiter, the volcanic moon Io spews material that fills this bubble. Scientists expected the icy moons of Uranus, Titania, Oberon, Ariel, Umbriel, and Miranda to do something similar, shedding water vapor or ice particles to fill the magnetic trap. But the instruments reported a vacuum. The magnetosphere was incredibly empty, cleaner than the space between the planets. Yet, simultaneously, the radiation detectors were screaming. They found radiation belts pulsing with high-energy electrons as intense as those at Saturn. This was a paradox. How could you have a vacuum magnetosphere with no source of plasma, yet maintain radiation belts so intense they should have burned themselves out in days? The scientific consensus that emerged from this conflicting data was bleak. Uranus was written off as a magnetic freak. The lack of plasma suggested the moons were geologically dead, frozen solid billions of years ago. The off-kilter field suggested the planet's interior was a sluggish, non-convecting mess. Uranus became the boring giant. For 38 years, that single, fleeting dataset defined our understanding. But in 2024, Dr. Jamie Jasinski, a space plasma physicist at JPL, decided to crack this cold case. He wasn't looking for a revolution. He was simply reanalyzing old Voyager data to prepare for future mission concepts. He started looking at the solar wind measurements taken by Voyager 2 in the days before it actually hit Uranus. As you may know, the solar wind is a stream of charged particles blowing constantly from the Sun, and it has weather, gusts, storms, and lulls. Jasinski noticed something critical. Just 2 days before Voyager's closest approach, the dynamic pressure of the solar wind jumped by a factor of 20. It was a massive solar storm, a high-speed stream of particles blasted from the Sun weeks earlier, finally catching up to the outer planets. Using modern computer modeling that wasn't available in 1986, the team simulated what happens when a solar storm of that magnitude hits Uranus. The results explained everything. Normally, the boundary of Uranus' magnetic bubble, the magnetopause, sits about 28 planetary radii out, which is roughly 430,000 miles. But the simulation showed that this solar wind pressure was so intense, it acted like a piston. It crushed the magnetosphere. During the flyby, the boundary was pushed in to just 17 radii. This catastrophic compression created the paradox Voyager saw. First, it caused a plasma purge. The magnetosphere was squeezed so hard that the internal plasma was physically pushed out the back, into the magnetotail. The vacuum Voyager saw wasn't natural. The system had just been emptied by the storm. Second, it created the radiation spike. The rapid compression energized the few electrons that remained, accelerating them to near-light speeds. This created the illusion of intense, long-lived radiation belts, when in reality, Voyager was seeing a temporary sugar rush of energy caused by the storm. The team calculated the odds of this happening. They analyzed 8 months of solar wind data around the encounter and found that the conditions Voyager 2 experienced occur less than 4% of the time. If Voyager had arrived just a few days earlier, it would have seen a completely different world. We had visited the planet on one of the worst weather days in a century and mistook a storm for the climate. This is the Solar Wind Mirage. So if we strip away the mirage, what does the real Uranus look like? This is where the science gets incredibly exciting. Without that crushing pressure, the magnetosphere would expand back to its normal size. It would look much like the magnetospheres of Jupiter and Neptune. Crucially, it would not be empty, it would be filled with plasma. And where would that plasma come from? The moons. This implies that the Uranian moons are not dead rocks. In the 1986 data, the lack of plasma was cited as proof that the moons were inactive. But under the mirage theory, the moons could have been active the whole time, puffing out water vapor. The storm just scrubbed the evidence away before we looked. This reopens the case for Titania and Oberon as ocean worlds. These moons are roughly 1,500 kilometers in diameter, large enough to retain internal heat and potentially liquid water layers beneath miles of ice. New thermal modeling suggests they could easily support subsurface oceans. If these oceans exist, they are likely leaking subtly into space, through micrometeorite impacts or slow seepage, creating a bubble of water plasma that Voyager missed. This changes the astrobiology potential of the entire system. Where there is liquid water, energy, and organic chemistry, there is the potential for life. The dead Uranus system is now a top-tier candidate for exploration, ranking alongside Europa and Enceladus. This discovery has poured gasoline on the fire for a return mission. The planetary science community has already declared a Uranus Orbiter and Probe, or UOP, as the highest priority flagship mission for the next decade. Launching potentially in the early 2030s, this massive spacecraft would do what Voyager couldn't: stay. It would orbit the planet, map the gravity fields of the moons to detect the wobble of liquid oceans, and drop a probe directly into the teal clouds to taste the ancient atmosphere. And here is the best part: the discovery of the Solar Wind Mirage actually makes this mission easier. We now know that the intense radiation belts were likely a temporary artifact of the storm. This means the spacecraft might not need the heavy, expensive radiation shielding required for Jupiter missions, allowing more weight for scientific instruments. This story is a profound lesson in scientific humility. For 40 years, we looked at a planet and saw a wasteland because we failed to understand the context of our data. Voyager 2 arrived for a dinner party 5 minutes after the house had been hit by a tornado, and reported that the hosts lived in ruins. Now, the ruins have been cleared away. The Uranus that awaits us is a vibrant, magnetic beast, surrounded by active, ocean-bearing moons. The mystery is solved, but the exploration is just beginning.